Welcome back to ECE 441A, 541A. This is the last week. We have two more class periods, and there's quite a bit to be done between now and Wednesday. Wednesday, homework 9, homework 10 is due, the project is due, teacher course evaluations are due, and the teacher course evaluations are good input for me, but I'm not seeing very many from you in terms of, I just see the percentage or the fraction of people that have completed. I don't have any idea who is in that fraction, but I appreciate those that have submitted. Maybe it's all the people that are here that have submitted that. I appreciate that. Today, in anticipation of the extra material that is due on Wednesday, there's office hours Monday and Tuesday that traditionally are not there from 12:30 to 2:30 if you have questions on homework 9 or homework 10. And the final exam is a week from tomorrow, which it starts at 10:30. It will be in this room, and it's from 10:30 to 12:30 on Tuesday. It's not a Monday, Wednesday, Friday. It's a Tuesday, just as a heads up. What I want to do today is continue with full state feedback, but we'll actually somewhat review for the final in this process. The final will be comprehensive, and it will be uniformly distributed across the entire semester, is the idea. It won't be focusing solely on the material since exam number 3. We'll try to distribute all of that material across the entire semester. We'll look at, maybe in jumping right into full state feedback, it was a little premature in the connection with what we've already done. So what I want to do after we briefly discuss full state feedback, the overview, I want to compare output feedback with full state feedback and get your input on how those are different or how they are the same. Full state feedback. The assumption is really that blue line, the thin blue line that's on the far right. Where is it pulling off? It's actually pulling off information prior to the output matrix. So we're assuming with full state feedback that we can go in and access every one of our state variables. That's the assumption. That we can measure position, we can measure velocity. It's not a linear combination of those. It's not the output, it's actually the state vector that we are measuring. We get the full state, we feed it back, or we weight that full state feedback vector with this matrix K, and that gives us our full state feedback. And if we want to inject a reference signal, we have a gain on that reference signal, which could be a matrix, but if our reference is scalar, if our reference input is scalar and our input is scalar, capital N is scalar, it's a 1-by-1 matrix. But this is now the picture of full state feedback, and that particular integrator block is a block of integrators. It's not just one integrator, it's a integrator for each one of the coordinates in that state vector, which I'm just collapsing into x prime going into the integrator, coming out is the state vector itself. That's the picture that should come to mind, and I've tried to identify the plant in this highlighted yellow, meaning that's the cheer that we've talked about. If you are comfortable with the transfer function, there is your transfer function, except with full state feedback, we actually need the state variables. We go in and measure those state variables, x1, x2, x3, etc., and feed those back, which is a little different than what we've been doing before. Again, full state feedback is potentially made up of two pieces. The feedback piece is really just the one piece. It's a linear combination of the state vector with this gain matrix K. That's what's linearly combining the state vectors. And then we have our reference input term, which is N times R of T. And our typical goal is we probably want the output Y to be following the input R. That's our typical goal. And if that's the case, ideally we want a DC gain of 1 between the input, the reference input R, and the output Y. Which means if we find this closed loop transfer function, T sub C of S, then K will adjust the dynamics. That's influencing the F matrix. That's our closed loop system matrix. And the capital N, which weights the reference signal going in, we can pick that to adjust the DC gain, or the value of that transfer function at S equal to 0, to have a value of 1. And that's now what we're trying to accomplish with full state feedback. We adjust the dynamics by picking K to change those dynamics from the open loop dynamics, which are governed by the A matrix. We move those around, and if our system is controllable, we can put those closed loop eigenvalues anywhere we want in this F matrix. That gives us a lot of freedom with this design approach, and then at the very end, we would adjust N, have some scaling value to make the DC gain of that closed loop transfer function equal to 1. That's our goal. So let's compare output feedback with full state, and we'll do it via an example, which you can generalize this to the generic case, but I think maybe it's more helpful to see it for a specific example. And in this case, this is our example that we started with last time, and here's where we can sort of review for the final exam. Here's an all-integrator block diagram that you might be given, and it may not be labeled. It may have the output labeled Y, maybe the input is U, but the state variables may not be included on the final exam. And the question could be, what's the state space representation? Or provide an A matrix, a B matrix, and a C matrix. And if the diagram is not labeled, then you assign those outputs of each integrator to be your state variables, which means I might have many different representations that are actually okay answers from the same problem. Because somebody might label the rightmost integrator's output x sub 1, somebody else might label it x sub 2, but you all, to get a correct result, would have how many state variables identified? Just 2. There's only 2 integrators. And the strategy is to assign the outputs of your integrators to be your state variables. Once you've done that, now you know what each of those derivatives are. x1 prime in this case is simply the input to that rightmost integrator, which when integrated gives us x1, and x2 prime is the input to the leftmost integrator, and that now, when integrated, gives us x sub 2. But once you've labeled those state variables, you should be able to create the A, the B, and the C matrix. And now that's time for you to fill in the blanks. What's in the first row of the A matrix? Or what's in the 1, 1 entry of the A matrix? x1 prime is really just x sub 2, isn't it? No direct input, no variable x sub 1 coming in to create it, so the top row we can actually complete in that way. So that now the A matrix just pulls off x sub 2, x1 prime is x sub 2, and there's no U directly driving the time rate of change of that first variable x sub 1. So now that's the top row, and that would give you 3 points out of however many points are possible for that particular problem. What's the second row? X1 is not coming in to influence X sub 2 prime. X sub 2 prime does have a piece from X sub 2, that's minus 1, and our input now is influencing the time rate of change of X sub 2. So that X sub 2 prime is minus X sub 2 plus U. And that's now the dynamic piece of this state space representation. What's the output matrix? 1, 0. And if we wanted, we could now fill in our cheer. C is now 1, 0. We have SI minus A, and if we subtract A from SI, we'll now invert that matrix and post-multiply that by B. And if you wanted to, you could then find that transfer function, which is now 1, 0. The inverse of that 2 by 2 is 1 over the determinant. And the determinant of a 2 by 2 is pretty easy. That's the product of the diagonals minus the product of the off diagonals. Then we multiply it by the cofactor matrix transposed, which really just exchanges the diagonals and negates the signs of the off diagonals, and multiply by B. The denominator simplifies to just this S times S plus 1, and now you can multiply those three matrices however you want. That curly bracketed piece is just a scalar. It's a polynomial, but it's now just a scalar, so you can slide it around wherever you want. And if we look at C times that SI minus A cofactor matrix, that's going to pull off the top row, and the B matrix is going to pull off the second column of that top row, meaning we're left actually with just this piece being picked out because of the combination of the 1, 0 in the C matrix and the 0, 1 in the B matrix. And that's now our transfer function, and you should be able to see that transfer function as far as what it is doing relative to a complex S-plane. And if you just had pure output feedback, unity output feedback, you could see the root locus of that system. Where are your poles for G of S? 0 and minus 1, where were your eigenvalues of the A matrix? It's upper triangular, they're on the diagonal, they're 0 and minus 1. That's a way to sort of check your work to see, have I done this even closely to be correct? But with output feedback, what does the block diagram look like? There's our system. It's the same system. It's just now with output feedback, it's in the adjective of feedback, output. We're only pulling off the output and feeding that back to create our closed loop system or our controlled system. The input U is going to be influenced by our controller, and the controller is going to, whoops, I'm mixing, this is the no-no that I really don't like you to do. So now, you know what? I'll make the necessary corrections. I'm going to put this into the frequency domain. Is everybody okay with what I've done so far? I missed a T. I can't miss a T. Okay, so now I have U of S. I have x sub 2 of s. Really, it's s times x sub 2 of s, and this is x sub 2 of s. This is s times x sub 1 of s. This is x sub 1 of s, and that's y of s. Now I'm just have s's. Oh, and my integrators, I'm now in the frequency domain. Interconnection structure hasn't changed. I've just now put my system into the frequency domain, and now the reason I became very nervous and anxious is when I wrote down that G sub C, I put it G sub C of S, and I was mixing time and frequency, and I didn't want to do that. But now I'm okay. Now this controller is going to be driven by this error signal between the reference input R and the output Y. And in this class, in Chapter 10, we've been concentrating on building these G sub C of S's. We could do that with root locus approach. We could do it with Bode plots. But this is what we were doing. We were measuring the output Y, only the output Y, which could be a linear combination of the state variables. It could be some combination of x1, x2, x3. But that's now being compared. The output's compared with the reference input. That error signal now is filtered or adjusted by our controller. And we've had many different controllers. We've had phase lead controllers, phase lag controllers, PI controllers, PID controllers. Those all fit in this G sub C of S block. And what are they? That's just a scalar transfer function if our error signal is 1 and our input is one-dimensional. And we're just filtering that error to drive our control into the system. Compare that or contrast that with full state feedback. Here is the same system, and now you should be comfortable with going time domain, frequency domain. We haven't done anything different to our system. It's just now how we want to control it. Now what do we do? Now we say our input U is going to pull off x sub 2 and weight that, let's say, with a k sub 2 and allow that to manipulate U. We are also going to measure x sub 1, which in this case actually is y, but that's okay, and weight that by k sub 1 and subtract that as a part of our U. And if we just wanted our system to respond to disturbances or bumps in our initial condition, this is all we would have to do if we didn't want to drive our system. If we just wanted it to respond to offsets in our state vector, we would maybe want y to always be 0. Then we've changed the dynamics of our system by the introduction of k1 and k sub 2. If we actually want to drive this system, if this is maybe a vehicle, we might want to inject a reference signal, weight that with this N matrix, and now we might want Y, the output, to track the input R. And we want to now compare this approach, Chapter 11, the full state feedback, with what we were doing in Chapter 10, which was output feedback. And if we're making this comparison, is this a fair comparison? Or if somebody's asking you, is this fair and why, maybe you want to be asking, what are the differences? What distinguishes the full state feedback configuration from the output feedback configuration? What are some maybe easily recognizable differences between this first block diagram and the output feedback case with this diagram in the full state feedback case. Pardon? In the full state feedback case, we're actually pulling out x sub 2, aren't we? We're assuming we can go in and access that second state variable. In the output feedback, we aren't doing that, are we? We're not going in and pulling off that internal state variable that we're assuming is available in full state feedback. In reality, it may not be. But we'll create, after this class, not this hour, but in a subsequent semester, you would create ways to create that state vector, estimators, observers, Kalman filters. You might have heard of these using different terminology, but we would create ways to measure the output y and reconstruct all of these state variables, x1, x2, x3, x4, and then we could use those estimated states to drive our system. But here we're not doing that. We're simply saying the comparison now between the output feedback and full state feedback, one of the first things to jump out at you is, well, in full state feedback, you're going in and accessing everything. Is that really fair? No, not really. You should be able to do more in terms of changing the dynamic behavior of your system with full state feedback versus output feedback. Full state feedback put us on the moon. Output feedback was introduced more in World War II times. I hope you kind of remember the decades that maybe those two occurred in. One was maybe in the 40s, one was in the 60s. So full state feedback was a newer concept, but it's come up with some maybe less than favorable behavior if you don't accommodate for it. And this one, full state feedback, is very sensitive to how you have your system modeled. What is the A matrix? What is the B matrix? What is the C matrix? The output feedback strategy is more robust to uncertainties in your system dynamics. If you don't know your system very well, full state feedback might sort of get you into trouble if you're not careful. But here, is this a fair comparison? Let me just say, no, not really. The full state feedback assumes we have access to the entire state vector, or the entire, yeah, that's fine, the entire state vector. And that actually might, in this full state feedback case, unless we have a really good knowledge of our A matrix, B matrix, and C matrix, this N matrix or variable may not give us the DC gain of 1 that we would like to have had if there's some uncertainties. And our tracking error might be bigger in full state feedback than in output feedback. How can we have in output feedback 0 error due to a constant input? What can we do in this system when we're using output feedback? What do we want to have? To have 0 error due to a constant input. To have Y tracking R without any error if we put in an R value of 5 or an R value of 6 and hold it there. We want to poll at the origin. Does this system or controller satisfy that, this particular case? Do we have a poll at the origin? In fact, we do. The system has a poll at the origin. And so now we are, with this configuration, guaranteed of having 0 error due to a constant input if we can stabilize the system. All we have to do is stabilize the system, and then we'll have 0 error. Now, the transient leading up to that 0 error may be terrible, depending on how we've designed our controller. But we're guaranteed that we will have 0 error due to a constant input. Let's go ahead and go through these two different designs based on some common design specifications. Suppose that we now have our design specifications. as follows. Maybe somebody says, let's have an air steady state due to a unit step equals 0. And that's kind of a no-brainer in the output feedback as long as we stabilize the system. The second design specification is, let's say that we have a 2% settling time of 1 second, and let's say that we want a percent overshoot of about 5%. Now, with those design specifications, how do we proceed? We want to design a controller for both the output feedback case, we want to build a G sub C of S, and we want to find gains for our K matrix and our N to achieve this in both of these cases. Based on these design specifications, what might we start doing to approach this? Can you start to obtain information that will guide your design process based on these design specifications? The first one, here you might say, oh, I need a pole at origin in the output feedback case, and what do you want in the state space approach? If you want 0 steady state error due to a constant input, what does that say in the state feedback case? Haven't covered this very much, so I can understand your head scratching. But we want to now pick N to give us a DC gain of 1 in our closed loop system. For this particular design spec, would say select that's a pretty one, isn't it? But if we clean that up a little bit, a T sub C of 0 of 1. And this would be for our full state feedback. And I'm assuming you're texting this, so it's FSF. I've never seen that, actually, so I don't even know that I would understand your text if you said FSF. Anyway, how do we translate a settling time and percent overshoot? What do we usually think about when somebody says a settling time of 1 second and a percent overshoot of 5%? Again, this can be a final exam review. How would you translate that, or what would be a final exam question? I feel like Jeopardy. I'm giving you the answer, 1% settling time and a percent overshoot of 5%. What's the question? And not is what is 1 second or what is percent, but what are the closed loop pole locations to achieve particular design specs? Meaning, somebody said sigma. I heard sigma. That's good. And percent overshoot. If we have a sigma, what else do we want? Zeta or omega sub d, anything to give us an angle. We have or theta. We just are naming Greek letters, but a lot of those would get you partial credit on the final. So how do we do, so what we want closed loop poles for an ideal two-pole system. What's a 2% settling time in terms of time constants? 2% settling time, that's 4 tau, or that's now related to our sigma, the distance we are into the left half plane, and we want that to equal 1. And now we have to go to this higher level math to figure this one out. No. Sigma is now 4. So now we know how far into the left half plane we want our closed loop poles. What about our percent overshoot? Does everyone have figure 5.7 memorized? Or the percent overshoot is 100 e to the minus pi zeta, or zeta pi over the square root of 1 minus zeta squared. That generates figure 5.7. So if you just needed to calculate that, you could plug in zeta once you know that from a 5%. But what's the zeta value for a 5% overshoot? I guess to get zeta we would need the other formula. Now we're really going to tax my recall. But the big thing here is to remember that square root. A lot of times people forget to hit the square root after they've calculated everything in brackets. But if we have the percent overshoot of 5, we plug in PO of 5, and now we take the natural log of that, square it, divide by pi squared, and if you don't know pi to many different digits, just say 10. Pi squared is roughly 10. That's close enough probably for what we need. And if we plugged of PO of 5, that's now 0.7. Or if you're playing around with Greek letters, what's this correspond to for theta? This is now 45 degrees in round numbers, right? All right, so what does that tell us we want for our desired closed loop poles if we have two closed loop poles? We have a sigma of 4 and a zeta of 0.7, or an angle of 45. There's where we might want to locate our closed loop poles. If we're doing the output feedback problem, have I used the adjective Cascade? That just sounds like I want to say that today. This is a Cascade controller. It just means that it's in series with the system itself in a unity output configuration. Our block diagram has that classical structure, and our G of S you could always find from the cheer, but we've already done that, and this was 1 over S, S plus 1. What kind of, or now do you remember how to type this system? What's the system type? What type of system is this? G of S equaling 1 over S times S plus 1 is what kind of a system? Type 1. And that's because of that pole at the origin. So this is a type 1 system. And that's what guarantees our zero error, zero steady state error due to a constant input. We're guaranteed of that if we have this unit output feedback. So our first design spec, our steady state error due to a constant, will in fact be 0 as long as we stabilize our system. If T sub C of S and that's one of our other cheers, wasn't it? I believe this was G sub C G over 1 plus G sub C G. As long as that's stable for our choice of G sub C, then we will have a 0 error due to a constant input. if you get nothing else out of this class, which I hope you get a little bit more than that, but you at least know how to draw S-plane diagrams, right? You know how to do poles and zeros, X's and O's. If somebody now on a Saturday afternoon starts talking X's and O's, you can pull out an S-plane, and they'll go, that's not what I was wanting. But maybe it is. Where do we do that? What do we have for this particular system? Where are our open loop poles? Where are X's? Zero and -1. Pardon? Go back up. We're texting. That's a closed loop TF. Now we have our poles, open loop poles identified. Where do we want our triangles? Where do we want our closed loop poles? And I'm giving no hints whatsoever in this discussion. Where do we want our triangles? Left half. I'll correct you on that one. And we want those at -4 plus and minus J4. Now, what would be a pretty quick controller to achieve your root locus branches passing through those triangles for this configuration? Where would you sprinkle down? You've also learned how to cook in this class with your zero shaker and your pole shaker. You can put that on your quiche if you want. You now have a zero shaker and a pole shaker. We want to put those down on this S-plane. Where do we put a 0? Probably cancel that -1, and I wanted that to be in red. So now I'm going to really... Okay, and now where do we put our pole? At -8. So we come over here to -8, wherever that is. Hope that's right. And we put our pole. And that's not right, is it? Are you counting? Are you kidding? There. It didn't look symmetric. Even though my diagram wasn't very accurate, it still didn't look symmetric. Now it looks better. So that now we have this branch coming in there, this branch zipping through there. They break halfway between, which in this case is at -4. And we adjust the gain. What's that red line indicate? What's the phase of this pole 0 pattern on that red line? What's the angle due to each of those poles and zeros in this configuration if you wanted the angle at that red line? So maybe I'm asking a question you've never heard me ask before, but what's the angle that defines our root locus? How do we draw these red lines? It's -180. Every point on that red line has to have an angle of -180. That's why it's there. That's this 1 at -180. So every point, if we looked at the angle contributions from those poles and zeros at any point of those red lines, it would be -180. What do we need to do to get to the triangles? Picked up part of our controller. What's left is K. And how do we find K? We use the magnitude condition so that we now have our G sub C times our plant. That magnitude has to equal 1, and then we will have our closed loop poles. That will give us this 1 plus k g sub c g equaling 0, which is what we want for our denominator polynomial. In this case, the s plus 1's cancel. We really don't need to worry about those, and we can solve for k, and we now have the magnitude of s plus 8 over 1. We really don't have any zero factors, and we want to evaluate that at s delta. So that now we have this equal to the magnitude of s, which is 4 squared plus 4 squared, times the magnitude of s plus 8, which is also 4 squared plus 4 squared square rooted. So when I multiply those together, I end up just with 4 squared plus 4 squared, which is 32. And my full state controller now, my controller in the output feedback has now been determined. What kind of a controller is this? If you had to name this with any more description, you could say, oh, that's a Cascade controller. But we could also call it something else. Is it phase lead or phase lag? This one is actually phase lead, isn't it? The 0 is closer to the origin than the pole, so this is actually a phase lead controller. This, we had a 0 here and a pole there. That's the phase lead structure. Phase lag is just the opposite orientation of the pole. A classical phase lag is a PI controller, and that has a pole right at the origin, and then a 0 on the left half plane. Let's do the full state feedback design and compare that with this one. This one wasn't very difficult, was it, to design? Why? Because we just had 2 poles, and it went together quite nicely. Let's look at our full state feedback design. It won't be very difficult either. And that's always the classical thing to make you nervous, right? If you say, oh, it's not very, or it's easily shown. That's usually when you go, whoa, but this one's really not that. What's our desired locations for our closed loop poles? Where do we want those to be? If we're comparing this design with the previous design, where did we have our closed loop poles before in the output feedback case? Where were our triangles? -4 plus and minus J4. We now want a desired polynomial to possess poles or zeros at those locations. There's a factor that has for its roots -4 plus J4, and we want another factor that has as its roots its conjugate, which is now -4 minus J4. And if we multiply this out, we can wisely sort of group these pieces together. We can take that piece, and what happens to the inner and outer piece if you're doing FOIL, multiplying a quadratic? First, inner, outer, and last. They cancel, don't they? Because we have a minus J4 and a plus J4. Those cancel, and now we're simply with minus J4 times J4. The minus cancels with the J squared, and we have 4 squared. Or we now have S squared plus 8S plus 4 squared plus 4 squared, or 32. What do we want that to be a part of? Or where do we want to end up with this desired polynomial? If we're doing a full state feedback, we want the closed loop system matrix to have that polynomial as its characteristic polynomial, or the eigenvalues of our closed loop system matrix. Our closed loop system matrix is F is equal to A minus BK, where you can go through the derivation, but now our A matrix was that, our B matrix was 0, 1, and our K was K1, K2. If we multiply that out, we haven't changed the 1, 1 entry, we haven't changed the 1, 2 entry, but the 1 in the B is saying, oh, you're going to modify what's in the second row. Now we have minus K1, and we have minus 1 minus K sub 2. That's now our F matrix. Whoa. And we now want the determinant of that, Si minus F, for an answer. We're looking at S and S on the diagonal, and now we subtract the F matrix. And compute the determinant of that 2 by 2 matrix. We have S times S plus 1 plus K sub 2 minus a minus K sub 1, or plus K sub 1. That's the determinant of that 2 by 2 matrix, where the 2 by 2 matrix was Si minus F, and F is our closed loop system matrix. If we now distribute that S, we have S squared plus 1 plus K sub 2S plus K sub 1. And how do we find K1 and K sub 2? This polynomial we want to equal our desired polynomial. So we want the linear coefficient to be 8 by the choice of K sub 2 and K sub 1. In this case, it's just K sub 2. And we want the constant coefficient to be 32. If we equate our coefficients, then the S1 coefficient says we have 1 plus K sub 2. We want that to equal 8. And the constant coefficient needs to be 32. And now we've computed our K matrix. That's K1, K sub 2, which is now this matrix of 7, 32. And that's how we would weight. What's K1 waiting? It's waiting for the end of finals week? No, it's a different choice of the word waiting. Not W-A-I-T, but W-E, right? So this is now weighting what? The first component of the state vector, and K sub 2 is weighting the second state to give us what would be our closed loop eigenvalues in the F matrix. Minus 4 plus and minus J4 by design. What's the only thing left to do? Find in. What is in? That now needs to be determined to make our DC gain equal to 1. I'll give you the punchline and maybe I'll fill in the gaps after class, but this actually produces an N of 32. See below. So I'll leave you in suspense, but we'll pick up somewhere close to here on Wednesday. But be warned that you have 2 homework assignments and a lab due on Wednesday in addition to your project if you're in 541.